I think therefore I'll call you to order and we'll start. We have two speakers tonight. The first is Andrew Thornett, who will speak about his home observatory and 3D mapping of hydrogen sources, if I've understood the talk correctly. The second talk will be Richard Knott, who will be talking about software for um, cosmic ray observing and muon counting. So, Andrew, the floor is yours. I'm not sure how much time you've been given, but I may call time if necessary.
Oh, that's probably a very good question. How long do you want me to take? I can alter it to suit. Give me an idea how long you want me to take.
Paul, I'm not
30,
sure what you've agreed.
yeah, 30, 40 minutes, and then we can take some questions, and then Richard, and then we come back to you, Andrew, to talk about your green bank observations.
Oh, you
We
want me to do
close
that
off.
in two bits, is it?
Yeah, we close off with that.
Okay,
Okay.
30 minutes each then, please, Andrew.
Okay. Righto.
And we are recording. It's
Okay.
all yours.
Yeah. Let me see if I can get this share business to work. If I share the screen, that's probably the easiest. Right. Can you see Litchfield Radio Observatory? Can you see that picture of a
Yes.
couple of uh,
Yeah,
uh,
good.
wrongly
Yep.
located aerials? I say aerials deliberately for the American contingent, just to irritate them. In the snow. I just like it in the snow. So I still think that if you're going to do something like radio astronomy, the really important thing is to give your back garden a really posh sounding name. And then when you order anything from any company, you've got to put it down that you're from Litchfield Radio Observatory, especially if you order it off AliExpress. It makes them think that they're selling to professionals. Anyway, so it's about my description. It's probably the best thing is I've got somebody who's still got their microphone turned on. Probably best if you could perhaps mute that, guys. So in the description, it said talking about my home observatory. I'm maybe more specifically going to talk about hydrogen line and Milky Way mapping tonight, if that's okay with you guys. So how see if we can get this to the next page. There we are. So for people who are not located in the UK, I'm located in Lichfield. So this is to orientation. This is actually the middle of England, with Wales on the left-hand side there on the map, and right in the middle we've got this large city called Birmingham, about 10 million inhabitants. I think it is somewhere around there. And just a bit north of that, on the rural edge, is Lichfield, a very ancient city with a very long history, and the Queen used to visit quite a bit. I remember seeing her at the railway station on one occasion. So it is some fields in the local area, but the whole general area is, as I say, around 10 million or so people, the Birmingham Black Country. So it isn't exactly radio quiet, but still, on the other hand, we're also not right in the centre of the city either. All of this business I'm going to talk about tonight, and the enthusiasm I've got for it, can be very much put at the feet of the Society of Amateur Radio Astronomers in America, SARA, and particularly their project called Scope in a Box. Now, one thing I would say our American colleagues do incredibly well is write manuals for things. Quite a lot of the American stuff seems to be deliberately aimed either at high school students, who are equivalent in the UK of sixth formers, or alternatively first year undergraduates at university. And so it's aimed at people with an interest, with some understanding, perhaps of physics at a school level or high school level, but with no particular knowledge of the area in question or of radios or anything like that. So the manuals speak in a way which treats people with respect, but also which is very clear, uses language which is understandable, and gives a process for doing things which is relatively easy to follow and actually works, which is saying something when it comes to radio astronomy stuff. So I am extremely enthusiastic about the different projects which American colleagues have put together, and combine those with the brilliant kit which the UK Radio Astronomy Association produces. And I think we're in a very very fortunate time for amateur radio astronomers. The other thing that's come alongside of this is the fact that equipment that used to be very expensive is now much cheaper to purchase. And there are also very specific equipment designed for amateur radio astronomers, which is now available off the shelf, whereas previously you had to get your old soldering iron out and make it yourself. So here's an example of something. So a company, which we'll come back to in a minute or two, because they feature quite strongly in this, called Neuralec, who are based in Canada. And one of the things they produce, not a lot of people know about, basically because it's not an absolute requirement. You can do other alternatives, but is that the sort of aerial or antenna component of this project you can just buy off the shelf if you want, and it's available in the UK or in America from Amazon. And they got a tuned 1.4 gigahertz or 1420 megahertz antenna here, which is about roughly 100 centimeters wide by 60 centimeters high. And as long as you orientate it in the right direction, you get a resolution that's equivalent to the 100 centimeters, i.e. to the 1 meter level. And as you can see there, it can be easily mounted on just a simple satellite tripod, as described in the Scope in the Box project. Now, the one in the Scope in the Box is actually a 2.4 gigahertz grid antenna, because at the time they wrote the manual, these ones weren't available. And also there are quite a wide range of choices of the 2.4 gigahertz antenna, and they're often a little bit cheaper. And they work quite well as well. It basically is essentially close to a harmonic of the 1.4 gigahertz, isn't it? And this is often because the question comes up when you buy one of these things, which direction do you put the waveguide? And as you can see there, that's done at 90 degrees. So the long axis of the waveguide is put in at 90 degrees to the long axis of the dish. And the dish itself, the long axis is orientated east to west. And this is to go with something called drift scanning, which we'll come back to in a minute or two. And if you just happen to make your own feed horn with a circle on it, Alex Pettit put this onto the SARA list. I thought it was a brilliant picture showing the orientation that should be at as well. Right, in terms of mounting these things, here's back to my pictures now. So here's a picture of my mount, or the mounts I make. As you notice, it's not particularly technological and doesn't require any particular skill apart from an electric screwdriver that acts as a drill as well, and a few bits of wood bought from my local hardware store, who got a section in their cutting room where they throw offcuts, and you can go and buy a pile of these things for a couple of pounds. So this is completely made of offcuts of wood from there and a few screws. And it's I said about drift scanning. So the way we do this is you just aim the aerial in any direction, because the software we're going to use in a minute will take any direction. And as the Earth rotates over 24 hours, the software will turn that into a series of measurements at that particular elevation, because you obviously give it the date and the time and where you're located on the Earth, and it makes those calculations for you. And then you can change the elevation, and you get a series of different measurements at different times, which then help you to produce your map. And I have this, as you can see, ultra high-tech method of changing my elevation by having a couple of batons with some holes in them, which I just change. I've made this of higher resolution recently by drilling more holes in the batons. There we are. Now, I mentioned Neuralec, coming back to them. So here we've got the thing on the left-hand side, which is really been a game changer to this whole business for amateurs. And this is the Neuralec Sawbird plus H1, which is specific filter for 1.4 gigahertz, which is plus or minus 50 megahertz. The Sawbird filter, which works quite effectively, takes about 40 decibels off outside of that range. But it also contains within it, because for this process you need to have some amplifiers as well, and those amplifiers in this case are actually included within the Sawbird, and it's actually got two amplifiers, one after the other. We've been discussing in SARA and the BAA new H-line group where we think the amplifiers are, and the best guess is one's before the filter and one's after the filter. I don't know if we know really. So the combination of two amplifiers and a filter gives you everything that you really need. So aerial plus a Sawbird, and then you need something to be able to turn this into a signal for your computer, and so you need a little receiver, and these new software-defined radios you can buy these days do the trick very well into whatever computer. And like most things radio astronomy, you don't need anything particularly powerful. Basically, any old laptop or computer you've got hanging around will do the trick, as long as you can leave it on 24 hours a day and somewhere to put it. So Sawbird will cost you, I don't know, about £50 in the UK. Your software-defined radio, about maybe £40. And if we go back to, if you want the off-the-shelf solution, they're currently running at about £130, £140 off Amazon. So basically, you can do the whole thing for around about £200 if you want to. It's worth saying that many people make their own aerials, and I have made one called a Cantenna, which is just made in an old coffee can. So you can do it very, very cheaply. So this shows the performance of the Sawbirds. Giving myself some actually kudos as a radio astronomer, I've actually used a VNA, a vector network analyzer, to produce these traces. Or more accurately, somebody else has told me how to use a vector network analyzer, and then held my hand while I did it. But still, it's I did it, and these are my different Sawbirds that I've got, showing that they all perform reasonably well. Now, when it comes to software, there's a couple of choices. So the one that is discussed in the SARA's Scope in the Box package is called SDR Sharp. Again, like most bits of software for what we do, guys, it's free, so just downloadable. And then there's this thing called the IF Average plugin, which is really important and allows you to collect and integrate the data over a period of time, like you might do if you're doing astrophotography. This picture shows the hydrogen line signal, which, given that the hydrogen line signal is at 1420.405, you'll notice on this plot is not at 1420.405. And we'll come back to that in a minute, because this is quite important in terms of how we do the mapping exercise. But it's worth noting here that hydrogen here expands all the way from 1419 or 0.20 there up to 1419.80 or 0.90. So it's spread over a spread of frequencies as well. And again, that's quite important. We'll come back to that in a minute. An alternative bit of software, which is one that I personally am extremely enthusiastic about, and I'm glad to see Ted on here tonight. So if anyone's got any questions about it, Ted's your man, because he wrote it. It's called Easy Radio Astronomy, which is a series of Python scripts, which not only collects your data for you, it then processes the whole lot, gives you about 250 plots, and it turns the whole business of hydrogen line mapping from a difficult exercise in actually collecting and processing the data, instead to a difficult exercise in understanding what the plots are telling you. And that's the difficulty with 250 plots. So what you do is you set up a meeting with Ted, who's really helpful, and spend 2 hours with him, and he'll tell you what your plots are showing you. This is Easy Col of the Easy Radio Astronomy suite, and showing data collection coming in, or actually data actually coming in. And again, this is showing that same process of, though it's 1420.405, in fact, in this particular case, the peak is sitting about there. You can see again, it's spread over a number of frequencies. Here, I've highlighted that on this particular graph here. And the reason is that hydrogen might be at one particular frequency, but by the time we collect it, it varies, and that's due to Doppler shift of the frequencies, either because the hydrogen cloud, which we're detecting the signal from, is either moving away from us or moving towards us. And when it comes to the Milky Way, that means different bits of the Milky Way are moving away or towards us, depending on where we sit within it. And that's the information that could be turned into information about velocity of the hydrogen, and then it's used to do your mapping exercise. This is, again, my results coming through, and you can see here that over 24 hours, one of the green, so to say, my data is the green stuff. The thing behind it is professional data, mapping out where you'd expect to see hydrogen in the Milky Way and elsewhere. And you can see from my data coming through that it's peaking up as it goes over the Milky Way, so confirming that it's collecting hydrogen. And you can see that at any given elevation, you've got one green line that's going over 24 hours. Or in fact, in my case, I collect it for a week and integrates it across the week. It improves the signal to noise ratio a bit. And then at different elevations, you can see we have a different line that's coming through. There's a limit to how much of this Milky Way you could collect from any given location on the Earth. And that's just simply because the location on the Earth we're at, some of the Milky Way we can't get to. And that will obviously affect how much map we can produce. And here's my map. So so in the background, you've got a map that I've nicked off Wikipedia. It's part of the Wikipedia Commons, so I'm supposedly allowed to use it. And I've superimposed on that the map that Easy Radio Astronomy has drawn for me. And you can see there that we seem to have, assuming that I have actually labeled these correctly, and I'm happy for anybody to correct me on this if they got the labels wrong. But if I've done correctly, I've got a very good capture of the Sagittarius arm, a decent capture of the Perseus arm, and possibly a more spurious capture of the other bits and pieces, which I think I've caught, but maybe with the eye of faith of it, perhaps. You will notice that because of the limitations of where we're located, and there's also some limitations to do with the mathematics that underpin the way the software analyzes it, we do quite well between 0 degrees, which is the horizontal line to the left, and 90 degrees, which is the vertical line straight up. But we don't do so well with the rest of the Milky Way when it comes to mapping it. Now, this is a diagram I've discovered and made a bit of an alteration, try and make it mine a bit. And I think it's quite powerful because it shows you somewhat the effect of trying to map the Milky Way, or for that matter, map anywhere else when you actually collect data using a radio telescope. So the sun's the yellow spot on the bottom that conveniently I've marked sun. And obviously that's where we're located. So from this point, relative to the sun, everything in our solar system is moving at 0 velocity as far as this map is concerned. But we have three different radial distances from the center of the galaxy, which are in different colors because it's quite often there is a different speed. Well, we know there's a different speed at different distances away from the center of the galaxy. So these are going to be moving at different velocities. But velocity obviously has a speed component, and it also has a directional component. When you add the directional component in, you can see that gas, which is moving at the same speed, may well appear as a different velocity when you actually measure it with your radio telescope. That's because velocity has two components at right angles to each other, and you only pick the one up with your radio telescope, which is in the line of sight. So in this case, for example, A and C do appear to be at a very similar place in this, well, at least in this case, a very similar velocity, which will be translated into a similar Doppler shift on our graph. But the sun and D are in a different location. And if we were looking, we've got E, but I haven't marked it. But if we had marked something behind the sun at the same level, then they may be appearing in a different place on the right-hand side, because the right-hand side is showing how this translates into what the radio telescope picks up. Now, when it comes to assessing dark matter, there's this very useful diagram, again, it's come off Wikipedia. So when you look at this, I want you to look at the center, the two galaxies have both got the center rotating at the same speed, but then look at the outside as well and see how that compares with the center. I hope you can see that the outer parts of the galaxy on the left-hand side are moving at a much slower pace than they are on the right-hand side. So on the left-hand side, we've got rotation as you would expect to see it without any dark matter. So here the velocity is falling off with distance from the center of the galaxy, whereas on the right-hand side, we've got something that's often described as a bicycle wheel effect, i.e. the outside is moving at the same speed as the inside or close to it. And that's the thing which is supposed to be the smoking gun for dark matter. And the explanation that's normally accepted is there must be a large amount of extra matter outside the galaxy that we are unaware of. To look at it another way, if you look at the graph on the left-hand side and just look at the inside bit rather than where it drops off completely, you've got the line that goes up. And when it gets to the top, there's a small plateau before it starts to drop. And the reason that is there is because at that point, there's still a large amount of galactic mass further out in the galaxy. So it doesn't have this dropping off effect. And again, so on the right-hand side, we're presuming that there is this extra mass outside of what we can see. On the left-hand side, we call that Keplerian motion. So that's following Kepler's laws. So if you look at this picture here, to start off on the left-hand side, we've got a graph which is Ted has produced, which isn't my data. That's come from stuff off Wikipedia and shows velocity of the various planets. And you can see as you get further away from the center of our solar system, the velocity of these planets drops off very quickly in an exponential fashion. That's Kepler using Kepler's rules. If you look on the right-hand side, this is my data. Now, in terms of what I'm able to measure, the sun is located at 8 kiloparsecs away from the center of the Milky Way, so we can't go any further out than that. And I can get into about 4 kiloparsecs. And you can see there that my line definitely is not following the same sort of dropping off effect as you see on the left-hand side with the Kepler's rotation. So therefore, it is much closer to a straight line, which is what you'd expect to see with the dark matter scenario. So I'm very pleased to be able to see that from my own backyard, this is all with the ptarmigan array scope, so it's 86 centimeters by 86 centimeters, that I've been able to detect the smoking gun for dark matter, as well as mapping out the Milky Way and weighing it at the same time, which is what this is. So that's actually quite a robust thing to do, actually, the weighing the Milky Way. It works very well, even if the rest of the stuff doesn't work. So this is me weighing the Milky Way out to kiloparsecs, showing a nice, relatively straight line. Now, Ted and I have been taking this further, and we've been using a program called RINERN 3D, which is, again, free. Ted produced another bit to Easy Radio Astronomy, which turns the data into something that can be read by RINERN 3D. And by using that, we've managed to do three-dimensional plots of the Milky Way. And here we are, using my data, showing a three-dimensional plot of those two main arms, as you saw on the 2D plot. I like it so much, I've given you a few more from different directions. And then I turned it into a bit of a video. That blows my mind that you can do this with an 86 centimeter aerial from your own backyard. Now, give Ted credit more. He's taken this further, and now Easy Radio Astronomy allows you to plot your data on a sphere. So now we're looking into the Milky Way from outside, or at least from the outside, out of elements of the universe, so quite a distance away from the Milky Way, I suppose. And you're looking down on it, and here's the Milky Way crossing the sky from the outside, mapped onto a sphere. And this is from sitting on the Earth, looking up at the Milky Way overhead. Yeah, the same data. Not quite as good as a picture taken with a camera, maybe, but still, this is a less than 1 meter radio telescope doing that mapping exercise. And here's a few more relief maps showing power levels mapped across on a drift scan. Oh, it's 3 days worth of drift scan. And a few more nice looking graphs. You can flatten those graphs and get similar effects to the 2D plots. This again using RINERN, and you can then see it from a different direction if you want to top right there. Now, just to show you some other ideas that I'm going at in the last 5 minutes. So Alex Pettit has produced this 13-element patch Yagi and sent me one of them, and so I'm trying to get that to work, and I'll bring that along to Yuccara later in the year so that you can have a look at it. And that's meant to provide a very small, easy to put together aerial, which can be used by people who want to get into the project, but have got perhaps very little space to keep it. Want to be able to put it away and pull it out without too much difficulty. And I've been spending this afternoon putting together a mount for that. Another thing that I've got is on the American eBay site, they sell these parabolic reflectors, about 1.5 meters wide, and they're covered with a mirrored mylar coating. And the idea is you put them up when you go out camping or whatever, and then you can put your kettle at the focal point and it'll heat your kettle for you. Believe it or not, it actually works. I managed to get one of these for £50 off eBay. Somebody's doing a house clearance out, one of them. The only problem is I also put a piece of cardboard up close to it and managed to burn a hole in the cardboard. And then it started burning my leg. So you have to do something about the mylar coating, which is a bit dangerous. So I initially sprayed some paint on it, which started coming off again. And I managed to find you can now peel the mylar off. So I recommend that if you do go on this route. But this is a very cheap way of getting a very decent sized dish. And in terms of making a waveguide, here's my antenna, which was initially used as an alternative small hydroscope and has now been used again to turn into a waveguide and detector for this particular scope. Now, when I first made this parabolic solar cooker radio telescope, it wasn't working, and I didn't know why. So I got this vector network analyzer, and we looked at the different components. I first of all found that the signal to SWR, on the antenna was quite good. So not really much of an issue. That shows, by the way, my probe inside it, which is made from a straightened paper clip. So this is the world's ultimate in cheap aerials. But what I didn't know was there are two different types of SMA connectors. You get this reverse polarity one. And what had happened is that on one side, I had the male RP SMA, and the other side I had the female SMA connector. So there was no actual central connector connecting the two together. So what is absolutely amazing is that I got any hydrogen signal whatsoever. And when we checked it with the nano of ENA, we were getting signal loss of minus 32 decibels. And when I managed to fix that connector problem, it went straight down to minus 2 decibels. And so all of a sudden, I'm getting a hydrogen line signal out of it now. And here we are. That's just showing the hydrogen line being detected by that particular telescope. And I did a little bit of an animation, which I thought was fun. Just wait a second. It will show you the hydrogen coming in. If you look carefully, you can see that the exact frequency of the peak has been changing. At the beginning, it was above the 1420.405 line, and now it's significantly below it. And this is, again, as you're getting to part of the Milky Way, which is moving away from us, and part of it which is moving towards us. Finally, I've tried adding in a cavity filter into this, which I got from China. I got some very good cavity filters, very cheap price. And we did some testing on this, and they are very good at adding filtering effects. But unfortunately, I think I'm running out of time now. But I perhaps we can show this. The thing to see is that compared to the previous one where you saw a very strong spike, here and you're seeing a small spike, unfortunately, cavity filter may provide extra filtering effects, but it actually also reduces the strength of the signal itself. So conclusion, the Sawbird H plus LNA is more than adequate on its own. Don't bother to add anything else in. Oh, and that's my next bit, which we're going to do at the end. Okay, guys, thank you very much indeed.
Thank you, Andrew. Any questions for Andrew on his observing suite?
I've got one question.
Go ahead.
All right, okay. On that little graph, which showed sort of hydrogen clouds A, B, C, D, E going off, there were two pink ones, which were roughly the same distance, and hence roughly the same shift. How do you actually tell which one was one side of the closest point and which one was the other side of the closest point, so to speak?
Ted, are you online? Can you answer the question? Are you happy to?
Yeah, that's the problem. From the data, you really can't tell.
Ah, right. Okay. That was what I was supposing, but Yeah. Okay.
And that's what the graph is trying to show. Exactly. But we can figure out some of the other ones anyway.
Yeah, because presumably you could do a vertical cut with a very sharp dish, but our size of dishes, that's a bit tricky.
Okay, can I have a quick question? You showed that the hydrogen line is quite broad, and that is you've attributed entirely to various things moving in different directions relative to us. How much does the actual Earth's rotation around the sun, around its axis, the sun's movement through the Milky Way add to that? Or do you compute it out?
Ted, I think all these questions are aimed at you.
Oh
I just
dear.
use your software.
Indeed, the Earth is moving around the sun, so that's a whole bunch of velocity. I suppose the Earth is rotating too, and we're going along for the ride. So there's a velocity. And indeed, the sun is moving around through its neighborhood of stars all on its own. So there's another velocity. But we can calculate those and remove them from the measurements that we pull down from the sky. And so, indeed, there is a correction going on. This all has to do with uh, velocity of the local standard of rest. So, VLSR is a whole subject described on the Ezra webpage with a video.
Thank you for that. I thought there was a name for it. Any more questions?
Yes, if I may. How do you
You're next, David.
how do you overcome, let's say, spurious signal input? Do you have filters in place to keep everything as centered as you can?
From my perspective, this is where the Sawbird plus or minus cavity filter question came in, because the Sawbird filters out plus or minus 50 megahertz from 1420. And it's got about 40 decibels reduction, which seems to work very effectively. We have a reasonable amount of RFI in this area, and so I was wondering whether the addition of an extra cavity filter, which actually has something like 60 or 80 decibels reduction, would actually improve things. But what I've proven is that adding that into the chain just decreases the signal itself so much that it that swamps any positive effects. I guess you could have an alternative amplifier set up and use the cavity filter, but Easy Radio Astronomy seems to do a very effective job of removing the effects of RFI, and I don't know how it does it. So again, I'll pass that on to Ted. What do you do in the software, Ted?
I think of RFI as two different effects. One is a noisy signal that's consistent on one particular frequency. So we can just say, okay, let's ignore that frequency. And you just cover it up with some data from another frequency. So you're just putting a blanket over the RFI. All right, that's one way. You can hide it. But every so RFI will come as a sharp burst. I think of a lightning strike, a big bunch of energy. And so I'm glad you're taking lots of data, because you can throw away that one data sample. And there are ways in Ezra to identify which ones to remove automatically. So two different coordinates there. It goes on forever.
I know that Ted has spoken to me at length about the different ways of doing it. And the way he really would like me to do it is to go through all the data and select out the really bad days and drop that, which would be the right way of doing it. I'm a lazy sod and I won't do it. So instead, we stick in, there are some optional parameters you can put into the processing commands, which will allow you to cut off spurious signals if there are outside certain limits, which can partially make up for incompetence in the user.
Now, Andy, you have a group coming up on on the 14th, I think it was, and that's what I'll be talking about, removing those spurious RFI signals rather automatically.
Yeah. So
Interesting.
Ted's going to come and speak to us for anybody else who's joining us.
Yeah, David, you had a question.
Oh yeah, thanks, Andrew. And Andrew, thanks. Your plot from, sort of the middle of the talk where you were fitting your data to what you might expect from a dark matter distribution. The earlier, or the your green data to the left fitted that blue line very closely with very little scatter. But then it started to diverge from it, again with very little scatter. And then there was a third region on the right where it started to scatter a lot more and became much more distributed. Could you explain what's going on there?
Let me just try and find the graph. Are you talking about this graph here?
Yeah, but with the blue line underneath it.
Blue line.
There was a version where it was fitted to a blue line. There, that's
This
it.
one.
So the first region follows very closely. Then you diverge, but with very little scatter, and then it starts to scatter a lot more. So what is that about?
There's, I mean, Ted can might want to wish to add something in a second, but this, of all the analysis that you do with the data on this, believe it or not, the mapping exercise seems to work relatively quickly and relatively automatically and quite robustly. The weighing exercise is just brilliant, and it just comes out with the rations. But the dark matter bit requires quite a bit of work to actually get the data in a way which can actually be processed to produce this map.
So Andrew, on the graph on the right, the left part of that blue line is missing just more data. And you're having a hard time up in north of London looking that far south towards the equator.
Yeah, I think what was being asked was why to the right of those dots, the line seems to go up and down a bit.
That's just probably just RFI. We could clean up the data a little bit.
But there's also that bit in the middle where it's very, very closely packed, but of a different gradient to the first part, which implies you're not dominated by noise, but it isn't agreeing with the earlier section for some reason.
You can see on the left-hand side there are a whole bunch of green dots, and they're very much in a straight line.
Yeah.
That's because we have a very difficult time getting some of our data, and so we draw a line where we see the data should be. There are some approximations using in this process, but what we're largely trying to do is show the shape of the curve is fairly flat, and that allows us to go on to the next stage where we're actually determining distance from the sun. And now we can actually plot it out in 3D space.
Okay.
Many steps to go through this.
Okay, I guess what's puzzling me is that the green points are so closely packed, and yet there's a sudden change in gradient, but where they seem to still be quite precise for some reason, and then they start to diverge. So
because we drew a line in the data, as opposed to where the data should be, we drew a line.
Okay. So between
I'll let you study the videos on the web.
Yeah, okay, never mind. I won't draw it out. Thanks.
No, I mean, this isn't. The software is not designed for research. It's designed to demonstrate the physics of people who are interested. And as Ted says, I mean, there are some inaccuracies here because we've been filling a gap in the data by essentially drawing a line between 2 points, and what you're picking up on is an error in the way that we drew the line.
Okay, so I mean, if I were to take the broad message that actually that is quite a good correspondence, and therefore you're detecting what you claim you're detecting, despite the nuances of small scale divergence.
Well, exactly, particularly with this graph, more than anything else in the software. This one is you can take the general direction of the graph, and you can see that it's not following Kepler's laws, and it's give or take following a straight line. I mean, so you could look at that, and you could have come back to me and said, "Oh, that's not a straight line; it's at an angle." But I wouldn't be prepared to read that amount of accuracy into this. But it's clearly not dropping off at an exponential.
Oh, no, surely, yeah, okay. So this is just some systematic effect that you haven't quantified yet.
To be honest, this debate is had with some other members of SARA. There are some members who are very keen on complete accuracy and at a detailed level, but it depends where you stand. Really, it's our hobby. We can, different people have different views, and none of them are right or wrong. But the idea is to demonstrate the main principles, really.
I think this graph would clean up just with more data.
Okay.
All right, thanks.
The engineering approximation of close enough for practical purposes.
Well,
there's a question on the chat about the 21 centimeter Yagi. Are there any links to that as a project or construction details?
Well, I don't know about construction details. Hang on, I will find for you. The Greenbank 20-meter Skynet telescope. Can you see that?
Mm-hmm.
Yep.
I always check with people these days because I did once have a presentation and I sort of got about a third the way through before people pointed out they couldn't see anything, which was a bit embarrassing. So, let me tell you a little story. So, my astronomy group, we have an astrophotography group, and a number of those people have decided there's too much light pollution in their backyards, so they're getting remote setups. And some of them, in fact, one group of them have actually got together, several of them, and they now have a telescope in Spain, which they rent time on together, and they bring in these incredible pictures on that Spanish telescope. So, wouldn't it be nice if, as radio astronomers, we could have our own remote setup, which would allow us to be a much more radio quiet area, a much bigger dish? Well, I'm showing you the picture of my remote telescope here, which is the Skynet 20-meter scope. Let's go big if we're going to have something. And in fact, all members of SARA, which I also am a member of, can actually do observations on this telescope because SARA actually purchased time. Or if you come along and you get somebody enthusiastic like me, you find that you run out of time and have to do a new contract and buy some more time. So I'm rather excited. Started to use a 20-meter scope to take some observations. And I won't go to the next page now. So here's things just showing the observations that have been taken, and anything that's got these are mine. Anything with the AMT on it is ones that I've taken. And so this is an opportunity to do something that my 1.5 meter scope can't do very easily, which is extragalactic sources. And you can see there I've chosen a number of galaxies to see what they look like when I take an observation with a 20-meter scope. And here are some of my observations. I've called it my AMT1 observing program. May as well be a bit posh here. And so these are 3 different galaxies, M101 obviously on the right-hand side, and a couple of others that have reasonable peaks, all in the hydrogen level. Sorry, all in hydrogen and stuff. And so these circles tell you a little bit about what you're seeing. So the galaxy itself in each of the 3 graphs is shown up by the dark blue oval, as you can see marked M101 on the right-hand side. But you'll also notice that all of them at around about the 0 mark have a peak either up or down, which represents the Milky Way. And this is because with a 20-meter scope, unlike with my 1.5 meter scope, even if you're looking out of the galaxy rather than along the plane of the Milky Way, there's still a bit of the Milky Way above and below us through the halo that we go, and this gets picked up in our observations if we've got something that's sensitive enough. So in all these observations, you get something around the 0 mark. Again, you've got an element of Doppler shift because you're going through hydrogen, which is some of it moving at different velocities or different speeds relative to us. And then you've got the hump that appears there that is of the extragalactic source that you're looking at. An interesting thing about this, if you look at M101, is you've got 2 peaks. And for so all of these particular observations and most of these galaxies, M31 is a bit of an exception, but pretty much every other galaxy you look at outside the Milky Way, the field of view of the 20-meter scope encompasses the galaxy near enough or fully. And you often end up with 2 peaks. And that's because part of that galaxy, well, the galaxy is rotating usually relative to us, and part of that galaxy is relatively moving at a faster speed in one direction relative to us than the other part of the galaxy. But those galaxies, on the whole, mostly, are moving away from us, and this is reflected in where those peaks are located relative to the Milky Way peak. And you can see that they're on all of them on the right-hand side. Again, this is another one, NGC 5457, which actually has a very pronounced hydrogen peak. This is a demonstration of the data that has been collected by the scope, and this time put onto a spreadsheet for graphing. Now, this is my first attempt, exceptionally low resolution attempt at mapping a galaxy outside of the Milky Way. You probably notice I'm a bit fanatical about trying to map galaxies. So in this case, it's M31, which isn't where the telescope is not able to encompass the entire galaxy within its field of view. So I've actually hit 5 different parts of the galaxy. And the first thing you notice is that all of these humps are on the left-hand side of the Milky Way spike. And because M31, of course, is unusual in that it's actually moving towards us, unlike most galaxies that are moving away from us. Also, if you look at these humps, you can see, because all velocity humps, you can see that some of them are closer relatively to the Milky Way spike than others are. And this again represents relative velocity of that part of the galaxy. And again, if you look at the one at the top and the one at the bottom has a sharper spike than the one at the top, which goes to a higher level. And this represents the tilt of the galaxy relative to us. So that even at this low level of resolution of 5 points for the galaxy, you're still getting some information coming out. So my next plan is to, if we get some more credits, is to actually get some more detail on M31 and try and get a more detailed map. And Ted's helping me by trying to write a routine to allow this to map these low resolution maps for me in easy radio astronomy. And if anybody's interested in contacting me, here's a few contact details. By all means, drop me an email, and there's my website address if you want to go on there and have a look more at what I'm doing. Okay, thanks very much. And of course, everybody is very much invited to join us on the 14th of April, if you wish, to our Hydrogen Line group, which is the second meeting only. And if you're interested, you don't have to be doing it, just be interested in it, then just drop me an email and I can send you the link. See if I can stop that. Okay, thanks very much.
Well, there's something certainly new to me, that you can do the same thing the optical people do, but with somebody else's radio telescope. That is impressive. Any questions for Andrew about using remote scopes? No, it's all quiet. Okay. Well, thank you very much, everybody.
There are actually quite a few questions on the chat, by the way.
Oh,
Are there? I can't see any on the chat.
just bear with me.
Will Ezra run on a map? God. Ted, I think you're...
I think some folks have tried. I don't have a Mac, so I can't prove it. Does that mean it's supported? I guess not, but give it a try. I haven't put it on a Raspberry Pi yet, but other folks have. So I think all these things are possible. Mostly Ezra is just running Python. When it talks to hardware with data collecting, that's where it might get trickier.
Yeah. With other questions, the 21 centimeter Yagi, well, that's part of Alex's design there, and I put 3 links onto the chat there that you can follow that to find out more about his project. If anybody wants to contact him directly, again, you can drop me an email. I can let you know his email address. Doesn't seem fair to put it on a a public meeting like tonight's, where it might be seen freely. But by all means, contact me and I can give it to you. And what else we got? What software are you using? Well, the two pieces of software which I mentioned were SDR Sharp and Ted's Easy Radio Astronomy. I'm a great fan of Easy Radio Astronomy, which is Ted very kindly tends to use me as a beta tester. So we muck around and come up with ideas, and he brilliantly writes for it, and I can try it out. And what sort of radio telescope do I have? Well, for this, I use two radio telescopes. The first one, which is still going, is a 86 centimeter by 86 centimeter ptarmigan Trifid dipole array, which is 4x4 band 3 military dipoles in it, with a corner reflector design on the base plane. So that's designed for military communication in the battlefield. They stuck it on a great big pole on top of a van. But that seems to perform at about the same level as a 1 meter dish in our tests. It's not particularly sensitive, but it is quite robust as a system to work. And it sits on our patio. My wife quite likes it because it doesn't look like a dish. And then I sneaked in when she wasn't looking, the 1.5 meter dish, and gave her a shock when she turned up. In fact, I was going to tell you tonight about the new 3 meter dish that I've got, because I was actually offered one of those free this week, and I was going to go up and collect it today. But then I pulled out last minute because I did some re-evaluation and realized that my marriage of just under 27 years was more important than a 3 meter dish. I've got to say it was a close run thing, though, because I could have done masers and I could have done all sorts of things with a 3 meter dish. But honestly, it's not the sort of thing I could have crept into the garden without it being noticed.
You could have done a load of welding to build a mount for it.
I'll knock a few bits of wood together. That was it up.
Fully steerable, a fully steerable mount. Okay.
Hi, my name is Adrian, and I'm also a SARA member. I just wanted to add, since Andrew just mentioned it, that 20-meter green bag telescope is also able to have a range of frequencies that it will allow you to pick up on the maser, the hydroxyl ion masers that are around 1600 megahertz, and I've been able to do that myself. And so it's that's another observation that can be made besides the 21 centimeter hydrogen emissions. And those are, for example, I've been able to visualize by using a raster scan of the green bank 20 meter of the masers from the molecular gas clouds in Orion, and that's pretty neat stuff. Anyway, since Andrew mentioned about the maser, it brought that to mind. I just wanted to let everyone know that that's a possibility.
Oh, I hope Rich is purchasing a lot of credits, because you just told me about how I can spend loads of them for Sarah.
Yeah, well, I'm kind of disappointed that they're out of time, because I wanted to do some studies, and I got in kind of late when I had some time to try to get on the Skynet, and I realized that, oh my gosh, they're down to like 5 credits, and a raster scan is you can get a raster scan that's not too horrible for about 120 credits. It does require more time, because you actually have to perform the raster, and each one of those scans, depending on the angular resolution that you want to move the telescope, it can take anywhere from 5 to 15, 20 seconds each raster, not the full scan, but each scan, individual scan. So that eats up a lot of credits, but that's an interesting project.
I see that Tom, the Sarah treasurer, is online with us tonight. I'm thinking that he's probably thinking to himself, "Oh dear." It's worth saying, everybody, that it used to be that if you weren't an American citizen, you couldn't use the 20 meter scope. it was limited to American citizens, but they seem to have changed the rules. I don't know when that was changed, but now you can, if you're a Sarah member, make use of it.
Actually, I popped up because I thought I ought to at least say that a new contract has been signed, the invoice has been received, and the check to the Green Bank Observatory is in the mail. It went in the mail on the 2nd of April. So more time should be available soon, and use it. I mean, as long as Sarah is solvent, and for today the Sarah is solvent, use it. I mean, that's what it's for. And I believe that the change to allow non-US members or non-US citizens happened in the last contract, which was why the last contract was a very long drawn out, because they had to make changes in the terms of the contract to allow non-US citizens, or maybe I should say US persons, not sure the legal definition there. But yeah, the still the requirement is you're not allowed to look at anything that's close to the Earth, nothing in low Earth orbit or even within inside the orbit of the moon. But yeah, it's there. We're trying to get more time in. We started working on that in January, and that's just the nature of the problem. And I'll go back to lurking here. I thought I'd at least say that it is going to happen soon, I hope.
Looking forward to it.
Thanks very much.
And
Tom,
of course,
before you stop
I can
lurking,
go back. And
Oh,
of course,
okay.
I can go back and look at the old data and cost Sarah nothing. Wendy?
oh, thanks. I was wondering, suppose you wanted to look at other people's data that's been collected by that telescope. Are there any restrictions? I mean, I would assume you'd have to ask permission, or how does that work?
My understanding is that all that data collected from Skynet is in the public domain, and I'm not even aware of whether there is any kind of lockout period from when the observation is made to when anyone is allowed to use it. If you
Yeah.
looked at NASA stuff, they always had a 1 year blackout period on the data, so that the actual people who wrote the procedure or the proposal and got the time, they had exclusive use of the data for a year, and then it became open to the entire public. And I assume with Skynet that all of it, that it goes into the public domain immediately, because I've never seen anything
No,
else.
no, it doesn't, Tom. I've had a look at it. So the Skynet takes its own observations, certain sort of public observations, takes from time to time. So there is a web page where you can access a number of observations. Anybody can access a number of observations that have been taken with the telescope deliberately for the purpose of public access. So anybody on this group could do it, or anybody else could access those. But apart from that, the observations that are taken by users are private and not in the public domain. However, SARA users are technically all the same user, which is why we have to put our initials after it to say who's done it. But it does mean that any SARA person who's got the login details for the 20-meter scope can access anybody else's data from another SARA member, but not from anybody else. However, and I forget how long it was, we were looking for some data, and Jason and I were looking at it to try and get some from the that he'd taken in the past. There's actually a limit to how long the data is kept on their website to access. Now, it might be that you can go back to the 20-meter scope folks and get that data, but it's certainly not available even with the login details after a certain number of months online. I don't know how many months that is. But the answer to Wen's question, as long as you've got the login details, anybody who's a SARA member, you would see, they'll be able to see their data, and that's why we put our initials after it.
The data within, since you have to log in under a specific username, and so all the data collected within any given username is open to all those logged in under that username. The data is not necessary. As far as I know, I first used the that 20-meter telescope back in 2021. I took a course that Green Bank offered. They call it the single dish school, and during that course, we had access to the 20-meter Green Bank telescope, and so that data is still there. And there's a long list of data that you can access, but there are some data points that are not. They're restricted. So not many, but the thing is, if you'll see a listing, each observation has a particular observation number. If you can see that number, you can access the data. And some of those numbers are not listed because they're restricted. And in that case, obviously you can't see that data. But definitely, if you're logged in under a particular username, everyone in that username login has access to all the data within that. And there's a significant amount of data that's also available from other login users. But again, if you can see the login, if you can see the observation data number, then you can click on that and get to the data from that. But as far as I know, the data goes back even before 2021 when I first used it. So I'm pretty sure it's not erased for in any given month. There's data there that's years and years old. You might not find the data for the observation that you're looking for. I tried to do that, for example, on the Maser observations from the Orion Nebula, and there really weren't any. A lot of people look at the Cygnus Masers, and that's what a lot of people focus on. It's a much brighter, stronger signal, and so that's the majority of the Masers you can see in that particular frequency range. But as far as I know, the data is not deleted or erased.
You might well be right, Adrian. I've just checked it, and in fact, the oldest data under the SARA account that's currently available on the 20-meter Skynet is the 27th of October 2018, which is interesting because what I said about not being accessible was based on the fact that Jason and I were trying to search for some data that he'd taken a year ago or a year or two ago, and we actually had the numbers of the observations and still couldn't find it on the search engine, which is weird. But there is in fact data on there right back to 2018.
Well, if he had logged in under a different user account, if that has changed, then that might be the possibility why you can't find it, because some of the observations from other users are restricted. But as far as I know, if you're logged in under a given user login, then all that data is available for as long as it's on the server. And as far as I know, it's not really deleted. So I'm not sure why.
It looks like you're probably right there. Yeah,
I'm not sure why he couldn't have found it. Anyway, it's a really nifty, fantastic privilege to be able to use that telescope. I mean, my God, 20 meters. If you think you have problems with your wife at 3 meters, can you imagine a monster like that in your backyard? That's impossible to comprehend.
It sounds to me like the perfect addition to the center of our lawn. I can't see the problem.
I'm going to ask the time-honored question now. I think it is time, gentlemen, please. Do you have homes to go to? I think that's been an extremely interesting evening. I'm going to call a close, or anybody who wants to watch the video back will be surprised at its length. But that's been an interesting evening and an interesting discussion. And thank you, everybody, for your time and enthusiasm.
Thanks, everybody.
Good night.
Thank you.
Yeah, thank you. Thank you very much.
Thanks, guys. Thanks, Paul, Andrew, and everybody else.